Today, let's look at some homework problems about pipelines. Pipeline problems are most often solved by using the energy equation. So for the first problem, we firstly balance energy between the upstream reservoir A and the downstream reservoir B to determine the velocity. So we write the energy equation first between the A and B. So HA plus PA divided by gamma plus V squared 2G plus HB plus PB divided by gamma plus VB squared divided by 2G plus head loss. This is equation 1. So we set the datum at the water surface of the reservoir B. So we will have that HB equals 0. Since the upstream water surface level is 8 feet below the summit, so this is 8 feet. And we also know the height from the summit to the downstream reservoir is 6 feet. So we can get that HA equals 52 feet. Because the two reservoirs are both exposed to the atmospheric pressure and the velocity had at the reservoir can be neglected. So we will have that PA equals PB equals 0 and VA equals VB equals 0. And then the head loss includes the friction loss and the entries loss and the exit loss. So HL equals HF plus HE plus HD. And we know we assume that frictional head loss is equal to the 2.5 times the velocity head. So the HF equals 2.5 times, 2.5 times V squared by 2G. And we know the entries is the squared edged. So we know the coefficient of the entries loss is 0.5 and the exit loss coefficient KD equals 1. So we will have that HL equals 2.5 V squared minus 2G plus V squared by 2G plus V squared divided by 2G. So now the equation can be written as 52 feet equals 2.5 times V squared minus 2G plus G plus V squared divided by 2G. So we can get that V squared divided by 2G equals 30 feet. Now, we balance the energy from the reservoir A to summit. So the equation is HA plus PA divided by gamma plus VA squared divided by 2G equals HS plus BS divided by gamma plus VS divided by 2G plus head loss is equation 2. And we know HA equals 52 feet and HS equals 16 feet. And the PA equals 0, VA equals 0. So in a pipe, VS equals V is equals V. And the total head loss includes friction loss and the entries loss. So HL equals entries loss plus friction loss. Since we know the entries loss, the entries is squared edged, so we know the coefficient of entries loss equals 0.5. So HE equals 0.5 times V squared divided by 2G. And we also know that the distance from the siphon entries to the summit is 1/5 the total siphon length. So now the friction head loss equals 1/5 times 2.5 times squared divided by 2G, because this is the total friction loss along the pipe. So yeah, and now the total head loss equals 0.5 times V squared by 2G plus 0.5 squared by 2G. And then now the equation 2 can be written as 52 feet equals 16 feet plus gamma plus 2G V squared plus 0.5 plus 0.05 times V squared divided by 2G, because we know we have calculated before that V squared divided by 2G equals 30 feet. So now you can get that the PS divided by gamma equals minus 4 feet. And now the pressure at the summit equals minus 34 feet times 0.3 pounds per cubic feet times 1 feet divided by 144 square inch. So PS equals minus 47 pound inch. So we know this value less than the minus point inch. So hence the cavation is a real cancer. So we have done this problem. For the second problem, we need to determine the maximum height above the aquifer that the pump can be placed without encountering cavitation. Let's look at what we know first. A pump will be used to remove 50 cubic feet per second of groundwater from aquifer and transport it to a water treatment plant. So we know the Q equals 50 cubic feet per second. And a 24-inch pipe is used and made of high density polyethylene with an entry screen and with the coefficient of entry equals 2.5. So we know the diameter equals 24-inch equals 2 feet. And we can get that the velocity V equals Q divided by pi times d squared divided by 4. So the velocity equals 50.9 feet per second. And the coefficient of entry equals 2.5. And we assume that the friction loss on the section side of the pump are negligible. So the friction loss equals 0. And now we're balancing energy from the surface of aquifer A to the section side of the pump S. So the energy equation is HA plus PA divided by gamma plus VA squared divided by 2G equals HS plus PST by gamma plus V squared divided by 2G plus head loss. And we set the datum at the surface of the aquifer A, so we know the HA equals 0. And the pressure head at the surface of aquifer is equal to the atmospheric pressure, so we know PA also equals 0. And the velocity head at the surface of aquifer can be neglected, so VA also equals 0. And in the pipe, Vs equals V. And we should avoid encountering cavitation. So the pressure head at the pump should be the minus 23 feet. We can find this value on page 99, the last paragraph in the textbook. And since the friction loss is 0, so the head loss equals entry loss equals 2.5 times V squared divided by 2G. So now the energy equation can be written at 0 feet equals HS plus minus 23 feet plus feet per square divided by 2G plus 2.5 times square divided by 2G. So we can find that HS equals 9.26 feet. So we have done this problem. For the third problem, we need to determine the maximum distance from the reservoir A that the pump could be installed without encountering cavitation problem. Actually, we need to determine this distance And let's look at what we know first. A pump is installed in a 100-meter pipeline to lift water at 20 degrees Celsius from reservoir A to the reservoir B, and we can see on the figure. And the pipe is rough concrete with a diameter of 80 centimeter. So we know this is a rough concrete. So rough concrete. So we can know the roughness height E equals 0.6 millimeter, and the diameter equals 80 centimeter equals 0.8 meter. And the design discharge is 4.5 cubic meter per second. So we know the Q equals 4.5 cubic meter per second. And now we can calculate the velocity equals Q divided by time d squared divided by. So the velocity is 8.95 meter per second. And now we're balancing the energy from reservoir A to the section side of the pump. Yes. So the energy equation is HA plus PA divided by gamma plus VA squared divided by 2G equals HS plus PS divided by gamma plus VS squared divided by 2G plus the head loss. We didn't set the datum, but from this figure, we know that HA minus HS equals 4 meter. And since the reservoir A is exposed to the atmospheric pressure, and the velocity at the reservoir can be neglected, so we know that PA equals 0, VA equals 0. In the pipe, the VS equals V. Since we should avoid encountering cavitation, so the pressure head at the pump equals minus 7 meter. We can find this value on page 99, the last paragraph in the textbook. And from the figure, we know the head loss equals the entries loss. This one. The entries loss and the friction loss. Since we know this is square-edged entries, so we know the coefficient of entries KE equals 0.5. So we can find the entries loss equals 0.5 times V squared divided by 2G. And according to the Darcy equation, we know the HF, this is HF equals F times L divided by D times V squared divided by 2G. And the length is the value that we need to determine for this problem. And we can find the friction factor on the MODI diagram. So since we know this is a rough concrete and we know the pipe's diameter, so we can find the reference height. Reference equals 0.6 millimeter divided by 800 millimeter. So the value is 0.0005. And Reynolds number equals d times v divided by kinematic velocity. So the value is 1.8 meter times 8.95 meter per second divided by the 1 times 10 to the power of -6 square meter per second. So this is because the temperature of the water equals 20 degrees Celsius. So our Reynolds number is 7.16 times 10 to the power of 6. So now we can from the MODI diagram to find the F. The F is the F is 0.0185. So now we can the equation is equation 1. So energy equation 1 can be written as 4 meter equals minus 7 meter plus 8.95 meter per second square divided by 2g plus 0.0185 times L divided by 0.8 meter plus 0.5 times 5 second square divided by 2g. So now we can find that the maximum distance equals 51.6 meter. So we have done. For this problem, a 14-meter long 4-inch commercial steel pipe connects reservoirs A and B as shown in this figure. We need to determine the minimum pressure P0 that would keep the pressure head throughout the pipe positive, and assume that all valves are fully open, bend losses are negligible, and the water temperature is 20 degrees Celsius. So I think the key to solve this problem is to understand this sentence. Keep the pressure head throughout the pipe positive. The most likely location for negative pressure in a pipeline is at the highest point in the system. So from this figure, we can see the point 4 and the point 5 are both at the highest location. So which point should we apply the energy equation between the reservoir A? We should choose point 5. Since it is further from the reservoir A, and therefore more head losses have occurred. So we write the energy equation between the reservoir A and the point 5. So HA plus PA divided by gamma plus VA squared divided by 2G equals H5 plus P5 divided by gamma plus V5 squared divided by 2G plus head loss. So Since velocity head at a reservoir can be neglected, so we know VA equals 0. And from the figure, we know the HA equals 10 meter and H5 equals 9.5 meter. And we know the PA equals P real. That's what we need to calculate. Since we need to determine the minimum pressure P0 that keeps the pressure head throughout the pipe positive, so we can get that P5 divided by gamma equals 0. And the head loss equals the entries loss, the friction loss plus the entries loss plus the valve loss. So according to the Darcy equation, friction loss equals F times L divided by D times V squared divided by 2G. And from the figure, we can calculate the L equals 10 plus 5 plus 5 plus 7.5 plus 5. So the value is 32.5 meter. And the diameter equals 4 inch equals 0.120 meter. And HE equals KE times V squared divided by 2G. And we know the entries is squared edged, so we know the KE equals 0.5 and the HV equals KV times V squared divided by 2G. We know this is the fully opened lifted type check valve, so in the textbook we can find that the KVA equals 12. So now this energy equation can be write as 10 meter plus P0 divided by gamma equals 95 meter plus V squared divided by 2G plus F times 32.5 meter divided by 0.102 meter times V plus 0.5 plus 12 divided by G. This is equation 1. So since the velocity is not available, so Reynolds number can be solved. But we know this is commercial steel pipe, so the reference height for the commercial steel pipe is, we know the E is 0.041 millimeter. So relative reference equals 0. meter divided by 1 meter. Sorry, this is 100 millimeter. So the value is 0 0.0441. So according to the Money diagram, we assume f equals 0.02. So now we can rewrite the energy the equation 1. So we get P rho divided by gamma equals 99 v squared divided by 2g minus 0.5. So this is equation 2. Then we balance energy from A to B to get velocity. So the equation is HA plus PA divided by gamma plus VA squared divided by 2G equals HB plus PB divided by gamma plus VB squared divided by 2G plus the head loss. We know the VA equals VB equals PB is 0, right? And we know the PA equals P0. And from the figure we know that HA equals 10 meter and HB equals 7.5 meter, and the head loss equals friction loss plus entry loss plus Valve1 loss plus Valve2 loss plus exit loss. So this is entry's loss, this is Valve1 loss, and this is Valve2 loss, and this is exit loss. Because the band loss are negligible, so the head loss equals this one. So we know HF equals times L divided D times V squared divided by 2G. For now, the L equals 14 meter, and diameter also equals 0.1 meter, and this HE equals KE divided by times, and we know KE equals 0.5. HV1 equals KV1 times V squared divided by 2G, and we know KV1 is a fully opened check valve, so the coefficient is 12, and HV2 equals KV2 times V squared divided by 2G, and we the valve 2 is a fully opened globe valve, so the coefficient of this loss is 10, and the exit loss equals KD times V squared divided by 2G, and the coefficient of exit loss equals 1. Because we assume f equals 0.02 before. So now we can get that 10 meter plus P0 divided by gamma equals 0.5 meter plus 0.2 times 40 meter divided by 0.102 meter times V squared divided by 2G plus 0.5 plus 12 plus 10 plus 1 times V squared divided by 2G. This is equation 3. And now we get P0 divided by gamma equals 31.3 times V squared divided by 2G minus 2.5. This is equation 4. So equation 2 and equation 4 simultaneously. So we solve equation 4 and equation 2 simultaneously. So we get we get V velocity equals 1.86 meters per second. Then we have the velocity value, so we can calculate the Reynolds number. So the Reynolds number equals D times V divided by kinetic viscosity. So this is 1 meter times 1.86 millimeter. Divided by 1 times 10 to the power of -6 square meter per second. So the value is 1.9 times 10 to the power of 5. So because we know the relative roughness equals 0.00441. So from the Modi diagram, we can find that the friction factor F equals 0.0185. So now we substitute the new F to equation 1 and equation 2. Equation 3. Equation 1 and equation 3. So we can get that P0 divided by gamma equals 19.5 V squared divided by 2G minus 0.5 and 0 gamma times 30.8 times V squared divided by 2G minus 2.5. So from these two equations, we can find that the new velocity also equals 1.86 meter per second. So we can conclude that the new F is okay. So therefore, P0 divided by gamma equals 19.4 times 1.86 millimeter square divided by 2g minus 0.5. So this value is 2.92 meter. So we can find that the pressure P0 equals 2.92 meter times 9,790 Newton per cubic meter. Since the water temperature equals 20 degrees Celsius, so the pressure value is 28.6 kilopascal. So we have done this problem. This is a 3 reservoir problem. Each reservoir's water surface elevation is given, and all the pipe data, lengths, and the diameters are also given. And we know all of the pipes are light ductile iron, so E equals 0.04 feet, and the temperature of the water is 68 degrees Fahrenheit. And we need to determine the flow rate in each pipe in this figure, and we also need to determine the elevation of the junction. If the pressure head at the junction is 30 feet. When we solve a 3 reservoir problem, it is advantageous to set the total energy elevation at the junction to match exactly with the elevation of the middle reservoir for the first iteration. So we'll show that Hj equals F1 5,100 feet. So now we know the Q2 equals 0, and for reservoir 1, the friction loss equals S1 minus Hj equals 2 feet. That's 5,120 feet equals 30 feet. Now, and we also know 30 feet equals F1 times L1 divided by D1 times V squared divided by 2G. And we can find this value from the problem. So value is F1 times feet and 3 feet times V squared divided by 2 times 3.2 V squared divided by feet square second. And this is equation 1. And we also know the E equals 0.0004 feet. So we can find the relative roughness equals 0.0013, and we assume complete turbulence. So from the MODI, we can obtain that from MODI. We can find that F1 equals 0.0127. And now we can calculate equation 1, and we can get the velocity equals 10.78 feet per second. And because the water temperature is 16.8 degree Fahrenheit, so we know the viscosity equals 0.000108 feet. So now we can calculate the Reynolds number is 2.97 times 10.6. And then now we also can find the new friction factor from the MODI, or we can use Swan-Lee-Jen equation. This equation is on the page 36 in the textbook. I prefer to use this equation to calculate the new friction factor. So the new friction factor new friction factor equals 0.0132. And then we calculate equation 1 again. We can get that velocity 1 equals 10.47 feet per second. And we also can calculate the new Reynolds number equals 12 times 10 to the power of 6. And then we can find the friction factor also equals the 0.0132. So now the friction loss is verified. So we can calculate the flow rate in the pipe 1 equals V1 times pi V1 squared divided by 4. So the value is 74 cubic feet per second. So similarly for level 3, the friction loss equals 518 feet minus 1 feet equals F3 times L3 divided by D3 times V squared divided by 2G, and so this equals F3 times 3,000 feet divided by 4 feet times V squared divided by 2 times 2.2 feet cubic. This is cubic square of so this is equation 2. we know the E divided by D3 equals 0.0001, and also assume complete turbulence. And we can find the F3 equals 0.012, and we can calculate the equation 2 and find that velocity V3 equals 22.38 feet second, and we know the viscosity 0.000108 square feet per second, and we can calculate the Reynolds number equals 8.3 times 10 to the power of 6. And then from the body, I'll also use a Swami-Jan equation. We can find the new friction factor equals 0.0123, and then calculate equation 2 again, and we found that velocity 3 equals 22.11 feet per second, and then we can find the Reynolds number, the new Reynolds number equals 8.2 times 10 to the power of 6, and the new friction factor also equals to the 0.0123. So the friction 3 is verified, so we can use it to calculate flow rate in the pipe 3. So Q3 equals V3 times pi times square divided by 4. So the value is 278 cubic feet per second. Now the total flow rate at junction equals Q1 minus Q3 feet per second minus 278 cubic feet per second. So the value is minus 204 cubic feet per second. So the too much outflow, the total energy had at the junctions is too high, and we need to guess the new total energy elevation. So after several trials, we found the total energy elevation should be 5,163.5 feet. Since the the pressure head at the junction is 30 feet, so we know the elevation of the junction is Hj minus 30 feet. So the value is 51 feet minus 30 feet. So the elevation of the junction is 5,133.5 feet. And then now, at this, when the total energy elevation is this value, in this situation, the Q1 equals 82 cubic feet per second, and the Q2 equals 183 cubic feet per second, and the Q3 equals 65 cubic feet per second. So the total flow rate at the junction equals 2 feet plus 1 feet minus 2 feet per second. So the value is 0. So the condition is satisfied. So we have done this problem. The last problem also is a 3 reservoir problem. We need to determine the surface elevation of this reservoir, the highest reservoir, giving the flowing water surface elevation and pipe data, the length data, and the diameter data. All of the pipes are of concrete, and the E equals 0.6 millimeter, and the complete terminus is assumed, and the actual elevation of the junction is 2049 meter, and the pressure at the junction is 97.9 kilopascal. So the first step, we need to determine the total energy level at the junction. So the total energy level equals Hj plus Pj divided by gamma plus Vj squared divided by 2g. From the problem, we know the Hj equals 2049 meter, and the pressure at the junction is 97.9 kilopascal, also equals 97,900 Newton square. Because the problem didn't give us the water temperature, so we show that the water temperature is 20 degrees Celsius. So now the specific weight is 90 Newton square meter. So we can calculate the pressure head. Velocity head at the junction is assumed negligible, so Vj equals 0. So now we can calculate the total energy level equals 2049 meter plus 10 meter, so it's 2059 meter. We know the water surface elevation at reservoir 2 is 2090 meters. So we know this value is higher than the total energy level at the junction. So the flow rate is from the reservoir 2 to the junction. So, and we will balance the energy between the reservoir 2 and the junction. So the energy equation is H2 plus P2 by gamma plus V2 squared divided by 2G equals J plus PJ divided by gamma plus Vj squared divided by 2G plus the head loss. This is equation 1. Since reservoir 2 is exposed to the atmospheric pressure and the velocity head at the reservoir can be neglected, so we know that V2 equals P2 equals 0. And from the problem, we know that H2 equals 290 meter. Since the minor losses can be neglected on the 3 reservoir problem, so that means the total head loss just equals the friction loss equals F times L divided by D times V squared, the velocity in the pipe, divided by 2G. And from the problem, we know L2 equals 1200 meter, and D2 equals 0.4 meter. And we also know that E equals 0.6 millimeter. So we can calculate the relative roughness is 0.0015, because the problem shows that the complete turbulence, so from the body we can find that the F equals 0.022. So now the equation 1 can be written as meter 2059 meter plus 0.022 times meter plus 0.4 meter times v squared divided by 2g. Now we can calculate the V in the pipe 2 equals so we can calculate the flow rate in the pipe 2 V times pi squared by 4. So the value is, so the flow rate in the pipe 2 is 0.382 cubic meter per second. And we also know the Hj is higher than the Ws3. So the flow is from the junction to the reservoir 3. And we will balance the energy between the junction and the reservoir 3. So the energy equation is Hj plus Pj divided by gamma plus Vj squared divided by 2g equals H3 plus P3 divided by gamma plus V3 squared divided by 2g plus the head loss. This is equation this is equation 2. And we know V3 equals P3 equals 0, and H3 equals 2092 meter, and the head loss equals friction loss in the pipe 3 5 times L3 these 3 v squared divided by 2g. We know from the problem, we know the length pipe 3 equals to 400 meter, and the D3 equals 0.5 meter, and E is 0.3 millimeter. So we also know E divided by D equals 0.0012. And from the Modi diagram, we can find the F equals 0.021. And now the equation 2 can be written as that meter equals 2020 meter plus 0.021 times meter divided by the 0.5 meter times v squared divided by 2g. And we can find the V now in the pipe 3 is 2 0.76 meter. So we can know the flow rate in the pipe 3 is V3 times pi. So the value is 0.542 cubic meter per second. Now, based on the mass balance at the junction, and the reservoir 1 is the highest reservoir. So the flow should be from the reservoir 1 to the junction. So now we can know that Q3 equals Q1 plus Q2, and we know Q3 equals 0.542 second, and Q2 is 0.382 cubic meter per second. So we can find that the flow rate in the pipe 1 equals 0.16 cubic meter per second. And now we balance the energy between the reservoir 1 and the junction. So, H1 plus P1 divided by gamma plus V1 squared divided by 2G equals HJ plus PJ divided by gamma plus VJ squared divided by 2G plus the head loss. This is equation 3. We know V1 equals P1 equals 0, and the head loss only equals the friction loss equals F times 1 divided D1 times square divided by 2G. We know the H1 is 1,900 meter, and D1 is 0.3 meter. The E equals 0.6 millimeter. So we can know E divided by D equals 0.002. And from the money, we can find the F equals 0.0235. And we know the Q1 equals 0.16 per second. So we can find that the velocity in the pipe 1 is Q1 divided by A1. The value is 2.26 meter per second. So now the equation 3 can be written as H1 equals 90 meter plus 0.0235 times meter divided by 0.3 meter times 2.26 square divided by the 2G. So now we can get the relevant elevation. It's 1 is 2097.7 meter. So we have done.